Welcome to our deep dive, into algorithms. We're exploring Introduction to Algorithms, third edition. Um, this book, it's a cornerstone of computer science and with good reason. When you think about it, algorithms are kind of like the technology we use every day.
Yeah, it's a fascinating point the book makes. We often think of hardware or, fancy user interfaces as technology, but algorithms are right up there with them.
I never really thought of it that way. Why do the authors say that? What makes algorithms so special?
So think about it this way. Like a really fast computer without good algorithms is like having, like a sports car, but not knowing how to drive stick shift. Like the
Hmm.
potential is there, but
Yeah.
you're not harnessing it. And algorithms are the driving skills that let us unlock the true power of computing.
Wow, that's a great analogy. So does this mean that understanding algorithms can actually make someone a better programmer?
Absolutely. Just like a skilled driver can maneuver through traffic smoothly, a programmer who understands algorithms can write code that solves problems efficiently and elegantly.
So algorithms are like the secret sauce for writing great code. What kind of algorithms are we going to be looking at today?
Well, the book covers a pretty wide range of algorithms, but we'll be focusing on some of the most fundamental ones, including sorting algorithms like insertion sort and merge sort. These are classic examples that illustrate, some key algorithmic concepts.
Okay, sorting algorithms. Tell me more about insertion sort. The name makes it sound pretty straightforward.
It is, in a way.
Yeah.
Think about arranging a hand of playing cards. So you start with one card, then you insert the next card into the correct position relative to the cards you already have. And you just repeat this process until all the cards are in order. That's the essence of insertion sort.
So it's like building a sorted hand one card at a time. That sounds pretty simple. What about merge sort? How is that different?
Merge sort takes a different approach. It's all about dividing the problem into smaller pieces, solving those pieces, and then merging the solutions back together. So imagine you have a huge stack of papers to sort. Merge sort would be like you divide the stack into smaller piles, you sort each pile individually, and then you merge those sorted piles back into one super organized masterpiece.
Okay, I'm starting to see how merge sort could be more efficient for larger sets of data. It's like breaking down a big task into smaller, more manageable chunks.
Exactly. And this divide and conquer strategy is a key concept in algorithm design. It's used in a lot of algorithms beyond sorting.
Divide and conquer. Okay. Now, the book uses something called pseudocode to describe these algorithms. What exactly is pseudocode? Is it a specific programming language?
Not exactly. Think of pseudocode as a way to express the logic of an algorithm in a way that's more human readable. It's not tied to any specific programming language, so anyone who's familiar with programming concepts can understand it.
So it's like a universal language for algorithms. That
Yeah.
makes sense. But how do we actually know if an algorithm is good or not? Like what makes one algorithm better than another?
Yeah, that's where algorithm analysis comes in. We need a way to measure how efficient an algorithm is, and that's where the RAM model comes into play.
RAM model. Is that related to the RAM in my computer?
It is related. The RAM model is a simplified model of a computer that helps us analyze algorithms. It assumes that basic operations like arithmetic, data movement, and control flow all take a constant amount of time. It's a way to abstract away from the complexities of real hardware.
So it's like a theoretical computer that we can use to test our algorithms.
Exactly. It gives us a common ground for comparing different algorithms and understanding how they scale with larger inputs.
Okay, that makes sense. So we've got the RAM model for testing, pseudocode for describing algorithms. But how do we actually measure efficiency? Is it just about how fast an algorithm runs?
Speed is definitely a factor, but it's not the whole story. We're also interested in how the algorithm's performance changes as the input size grows. That's where something called asymptotic notation comes in.
Asymptotic notation, that sounds pretty technical. What does it mean, in simpler terms?
So imagine you have two cars. One is a chippy little sports car. The other's a big, powerful truck. For short distances, the sports car might be faster, but for long hauls, the truck's power and efficiency take over. Asymptotic notation helps us compare algorithms in a similar way, focusing on how they perform as the distance, the input size, grows.
Okay, so it's not just about speed, but also about how well an algorithm scales. Does that mean that some algorithms are better suited for certain types of problems?
Absolutely. Just like you wouldn't use a sports car to haul a heavy load, you wouldn't use an inefficient algorithm to process massive data sets. Asymptotic notation helps us, choose the right tool for the job.
Okay, I'm starting to see the bigger picture here. Now, the book uses those symbols like big O and big omega. What do those mean?
Yeah, those symbols represent different types of asymptotic bounds. Big O notation describes the upper bound of an algorithm's growth rate, meaning it won't perform worse than that. And big omega notation describes the lower bound, meaning it won't perform better than that.
So it's like setting boundaries for how efficient an algorithm can be, but why is this important in practice?
Well, it helps us understand how an algorithm will behave as the input size grows, even if we don't know the exact details of the input. It's like knowing the fuel efficiency of that truck, even if you don't know the exact route. You can estimate how much gas you'll need for a long trip.
That's helpful. Now, the book also mentions logarithms. Why are those important in algorithm analysis?
Logarithms often pop up when we're dealing with algorithms that repeatedly divide a problem in half, like merge sort. They capture the idea of how many times can we divide something before we hit the bottom.
So it's like measuring how many times you can fold a piece of paper in half before it becomes too thick to fold anymore.
Exactly. And the book uses logarithms to describe the efficiency of those divide and conquer algorithms.
This is fascinating. It feels like we're uncovering this hidden language of algorithms. But I have to admit, some of this math is starting to make my head spin.
Don't worry. The beauty of this book is it introduces these concepts gradually, building on each idea. It's like learning a new language. You start with the basics, and you gradually build up your vocabulary and understanding.
That's reassuring. What else is on our algorithmic adventure today?
Well, we've talked about analyzing algorithms, but we haven't really talked about designing them. And one of the key principles in algorithm design is recursion.
Recursion, I've heard that word before. It sounds a bit like a snake eating its own tail.
That's actually a pretty good analogy. Recursion is the idea of solving a problem by breaking it down into smaller subproblems that are similar to the original problem.
Yeah.
And you keep breaking it down until you hit a simple case that you can solve directly. It's like those Russian nesting dolls.
Yeah.
You open one to find another, and another, until you reach the smallest one.
So it's like solving a puzzle by breaking it down into smaller puzzles that are easier to solve.
Exactly. And recursion is a powerful technique used in a lot of algorithms, including merge sort, which we talked about earlier.
So merge sort uses both divide and conquer and recursion. It's like a double whammy of algorithmic efficiency.
You got it. And recursion is a fascinating concept that we'll explore in more detail as we delve deeper into the book.
This is all so amazing. I'm starting to see how algorithms are like the building blocks of the digital world, and I'm excited to learn more about the different tools and techniques that computer scientists use to design and analyze them.
Well, get ready for an even deeper dive, because we're just getting started. We'll be back to explore even more fascinating concepts from introduction to algorithms.
Welcome back. Before we were talking about recursion and how it can be used to solve problems by breaking them down into smaller, similar subproblems. It's a powerful concept, but I'm still trying to wrap my head around it.
Yeah, it can take some getting used to. One way to think about it is like writing a set of instructions for someone to follow. But within those instructions, you tell them to refer back to the original set of instructions for certain steps. It's like a loop within a loop.
So it's like those choose-your-own-adventure books where you jump to different pages based on your choices, and sometimes you might end up back on a page you've already visited.
Exactly.
Yeah.
And just like those books need a way to eventually end, a recursive algorithm needs what's called a base case. It's a condition that stops the recursion, prevents it from going on forever.
Ah, so it's like having an escape route in a maze so you don't get stuck in an endless loop. That makes sense. But how does recursion actually work in practice? Can you give an example?
Sure. Let's go back to that merge sort algorithm we were talking about earlier. Remember how it divides the list into smaller sublists, sorts those, and then merges them back together? Well, the sorting of those sublists can be done recursively.
So each time we divide the list, we call the merge sort algorithm again on those smaller lists.
Precisely. And we keep doing that until we get down to lists that contain only one element, which are already sorted by definition. That's our base case.
I see. So it's like a cascade of merge sort operations, each one working on smaller and smaller pieces of the original list. And then we merge all the results back together like a puzzle.
That's a great way to visualize it. And this recursive approach is what makes merge sort so efficient for larger data sets.
Okay, I think I'm starting to get the hang of recursion now. Now, the book also mentions something called dynamic programming. How's that different from recursion?
So dynamic programming is a related technique, but it's more about optimizing recursive algorithms by avoiding redundant calculations. It's like remembering the answers to subproblems you've already solved, so you don't have to waste time solving them again.
So it's like having a cheat sheet for your recursive algorithm.
Exactly. Like if you're navigating a maze, dynamic programming would be like keeping track of the best routes you've found, so you don't keep retracing your steps.
That's a great analogy. It makes me think about those GPS navigation apps that calculate the fastest route based on traffic conditions. Are they using dynamic programming?
They could be. A lot of optimization problems, like finding the shortest path or maximizing profit, they can all benefit from dynamic programming techniques.
This is amazing. It seems like algorithms are everywhere, working behind the scenes to solve problems we encounter every day.
They really are. And understanding them gives us a deeper appreciation for how things work and how we can use these techniques to solve our own problems more effectively.
Speaking of problem solving, let's talk about data structures. I know this book covers a lot of them, from stacks and queues to trees and graphs. What are data structures exactly?
Think of data structures as ways of organizing and storing data in a computer so that we can access and manipulate it efficiently. Different data structures have different strengths and weaknesses, making them suitable for different tasks. It's like having a toolbox with different tools. You choose the right tool for the job.
So if algorithms are the recipes, data structures are the ingredients.
That's a good way to put it. And it's just like a good chef knows which ingredients to use for different dishes, a good programmer knows which data structures to use for different problems.
Okay, let's start with some of the basic ones. What are stacks and queues?
Imagine a stack of plates. You can only add or remove a plate from the top. That's the essence of a stacked data structure. Last in, first out. Queues, on the other hand, are like a line at a grocery store, first in, first out.
So stacks are like those precariously balanced piles of books on my desk, and queues are more like an orderly line of people waiting for a bus. Got it. But when would you actually use a stack or a queue in a program?
Stacks are great for things like undoing actions or keeping track of function calls. Imagine a text editor's undo feature. Each action you take is pushed onto a stack, and when you hit undo, the last action is popped off the stack and reversed.
Ah, so it's like rewinding a tape, going back step by step.
Exactly. Queues are useful for managing tasks that need to be processed in a specific order, like print jobs or requests to a web server. They ensure that everything is handled fairly and in the order it arrived.
So stacks and queues are all about managing order and access to data. What about linked lists? They sound a bit more, well, linked.
They are. Imagine a chain of paperclips where each paperclip holds a piece of data and a link to the next paperclip in the chain. That's a linked list. It's a flexible way to store data because you can easily insert or remove elements anywhere in the chain.
So it's like a treasure hunt where each clue leads you to the next one. And if you want to add a new clue, you just adjust the links. But are there different types of linked lists?
There are. In a singly linked list, each element only knows about the next one in the chain. But in a doubly linked list, each element also knows about the previous one, making it easier to traverse the list in both directions.
Ah, so a doubly linked list is like having a two-way street, while a singly linked list is like a one-way street. You can go back and forth more easily with a doubly linked list.
What about trees? Are we talking about like family trees or something more metaphorical? More metaphorical, but the family tree analogy isn't too far off. Imagine a tree with a clear top knob, the root and branches that lead down to other nodes, each holding data. These rooted trees are great for representing hierarchical relationships.
So a file system on a computer could be represented as a rooted tree, with the root being the top-level directory and the branches representing folders and files.
Exactly. And there are different types of trees, like binary trees, where each node has at most 2 children, and n-ary trees, where each node can have any number of children.
Okay, so trees are all about representing hierarchical data. Now, I've heard of binary search trees before. Are they related to those binary trees you just mentioned?
They are. A binary search tree is a special kind of binary tree that makes searching for data very efficient. It's organized in a way that ensures all the values to the left of a node are smaller and all the values to the right are larger.
So it's like having a phone book where the names are already sorted alphabetically. You can quickly find the name you're looking for by repeatedly dividing the book in half.
Exactly. And this divide and conquer approach is what makes binary search trees so efficient for searching, inserting, and deleting data.
Now, this is bringing back what we discussed earlier about the importance of choosing the right data structure for the job.
Absolutely. If you're dealing with data that needs to be frequently searched, a binary search tree can be a great choice. But if you need to process data in a specific order, you might opt for a stack or a queue. It all depends on the specific requirements of your program.
Okay, I'm starting to see how data structures are like the foundation for building efficient algorithms. They provide the framework for organizing and accessing the data that our algorithms operate on.
That's a great insight. And as we continue our exploration of Introduction to Algorithms, we'll see how different data structures and algorithms work together to solve a wide range of computational problems.
This is all so fascinating. I'm starting to see the world through an algorithmic lens, noticing patterns and processes everywhere.
That's the beauty of studying algorithms. It opens up a new way of thinking and problem solving. And as we delve deeper into this book, you'll gain even more insights and tools that you can apply to your own work and understanding of the digital world.
Welcome back to our deep dive into algorithms. We've talked about so much already, like sorting, searching, recursion, and dynamic programming, and even data structures. It's really cool to see how all these concepts are connected, and how they build on each other.
Yeah, it really is. It shows how elegant and powerful computer science can be.
Hmm.
These ideas, they might seem a bit abstract, but they have real-world applications that affect us every single day.
Absolutely. Before the break, we were discussing how different data structures are kind of like specialized tools for organizing and accessing data. And you mentioned stacks, queues, linked lists, and trees. What other data structures are there?
Well, one that's super important is the hash table. It's made for like really fast data retrieval. Imagine a library where each book has a unique call number that tells you exactly where it is on the shelves. A hash table works kind of the same way.
So instead of searching the whole library, you just go straight to the shelf where the book is. That sounds really efficient.
Exactly. You give the hash table a key, which is like the book's title, and it uses a special function called a hash function to calculate a unique index, which is kind of like the call number that tells you where to find the data you're looking for.
So it's like having a super efficient librarian who knows where every book is in the whole library. No more wandering around lost in the stacks. But what happens if two books end up with the same call number?
That's called a collision. And
Yeah.
hash table designers have to like plan for that. There are a couple of different strategies to handle collisions, like chaining, where you make a list of all the items that have the same hash value, or open addressing, where if the spot you want is taken, you just find another spot for it.
So it's like if two books have the same call number, maybe we put them on a special shelf nearby or put them on a waiting list.
Yeah, exactly. And these collision resolution strategies are important because they make sure the hash table is still efficient even when there are collisions.
Hash tables sound really powerful. What are some real-world applications for them?
Oh, they're used all over the place, anywhere you need fast data retrieval. For example, databases use hash tables to quickly find records based on a search key. Compilers use them to store information about variables and functions, and even internet routers use them to efficiently send packets of data.
Wow, so hash tables are like the unsung heroes of the digital world, just working behind the scenes to make everything run smoothly.
Yeah, they really are. They're super efficient, making them an essential tool for computer scientists.
Okay, so we've talked a lot about data structures. Now I want to hear more about those graph algorithms you mentioned earlier. They sound pretty interesting.
Graphs are really cool because they're so flexible. Think of them as a way to represent relationships between different things. So like imagine a network of cities that are all connected by roads. Each city would be a vertex on the graph, and each road would be an edge that connects those vertices.
So it's like a map, but it shows not only the locations, but how they're connected.
Exactly. And graphs can show all sorts of relationships, not just physical ones. For example, a social network could be shown as a graph where every person is a vertex and friendships are the edges that connect them.
I see. So graphs can be used to model all sorts of complex systems and relationships. What are some algorithms that we can use to analyze and work with these graphs?
Two of the most important graph algorithms are breadth-first search and depth-first search. Think of them like different ways to explore a maze. So breadth-first search goes through the maze layer by layer. First, it looks at all the paths that are one step away, then two steps away, and so on. But depth-first search is different. It chooses one path and follows it as far as it can before going back and trying another path.
So breadth first search is like systematically checking every room in a house, and depth first search is like following a hallway to the end and then turning around to try another hallway.
Yeah, that's a great way to put it. And we can use these search algorithms to solve lots of different problems, like finding the shortest path between 2 points, or checking if a graph is connected, or even to find groups within a social network.
Wow, so graph algorithms are like having a special ability to understand complex networks. I know the book also talks about minimum spanning trees and shortest paths algorithms. Are those related to graph algorithms?
Yeah, they are. A minimum spanning tree is like finding a way to connect all the vertices in a graph using the smallest total weight of the edges. It's like if you were trying to build a road network to connect a bunch of cities. A minimum spanning tree would show you the cheapest way to connect all the cities without building any unnecessary roads.
It's like being careful with your money, but still making sure everyone's connected. What about the shortest path algorithms?
Shortest path algorithms are all about figuring out the most efficient way to get from one vertex to another. Like, think about those GPS navigation apps, the ones that calculate the fastest route from where you are to your destination. Those are using shortest path algorithms to find the best route.
So it's like having a digital guide that always knows the best way to get where you want to go. That's amazing.
Hmm.
But we've only just started to look at what this book has to offer. There's still so much more to learn about algorithms.
You're right. We've only talked about a few of the most important concepts, but this book goes way deeper, covering all sorts of advanced algorithms and data structures and the techniques for designing algorithms.
It's like we've opened the door to a whole new world of thinking about computers and how to solve problems.
Exactly. And this is just the beginning of the journey. As you continue to learn about algorithms, you'll find new ways to approach problems and to design efficient solutions. You'll also better understand those complex systems that are all around us.
Well, I'm definitely excited to keep learning. This deep dive has been an amazing adventure into the world of algorithms. If you're listening, I really encourage you to check out the book Introduction to Algorithms and start your own adventure exploring this really important field.
And remember, algorithms are everywhere.
Mhm.
Once you know what to look for, you'll see them in everything from the technology you use every day to the way our society works and even in nature.
So keep learning, keep exploring, and keep pushing the boundaries of what's possible with the incredible power of algorithms. See you next time.